Okay, so here we have the question, f is a function from R2 to R such that fxy is given to be x minus y whole square times sine of 1 by x minus y. And we're asked to check if it is continuous and if the partial derivatives exist, if the partial derivative is continuous and if it's differentiable. Let's start off with the first option. So it asks if f is continuous. So how do we check it? Limit x going to 0, y going to 0. We want limit of this to be equal to f of 0 comma 0. But what is f of 0 comma 0? That is nothing but equal to 0, right? Now this is what we have to check. Let's do. So we have limit x and y going to 0. We have x minus y squared sine 1 by x minus y, right? This is what we need to compute. Now observe that both of these terms are positive, so we can write 0 less than equal to modulus of x minus y squared sine 1 by x minus y. And since sine of anything is less than equal to 1, we can see this is less than equal to x minus y squared. Now observe, now if I apply limit, what do I get? I get 0 less than equal to limit of x comma y going to 0 modulus of the function fx comma y less than equal to, and this will be limit x comma y going to 0 x minus y squared, which is nothing but 0, right? So by sandwich rule we have that limit of the modulus of fxy is 0, right? So now by sandwich rule or sandwich theorem, we have that the limit of the modulus of fx comma y is 0, but that means that the limit of fx comma y is also equal to 0, right? So what do we have? We have that the function is continuous at the point 0 comma 0. Next option asks us to check whether the partial derivative exists or not. So how do we go ahead? So to check partial derivative, what do? We look at, so to check partial derivative of f with respect to x, what we do is we look at the limit of, so we need to check this at the point 0 comma 0, right? So what we do, we produce a small increment h in the x coordinate, keep y the same, minus f of 0 comma 0, and then we divide the whole thing by the small increment, and the small increment will go to 0. This is what. So if this limit exists, then we say that the partial derivative of f at x exists, right? So what will this be? So we know this would be h square sine 1 by h. This would be 0 by h. This will be nothing but h sine 1 by h. Now observe that if I take the modulus of this, right, then this will be less than equal to modulus of h, because sine is less than equal to 1, and it will be greater than equal to 0. So again by sandwich rule, what do we have? We have that limit of this thing, this increment or or we can say that, or we can directly say that fx exists. Not just that it exists, we can also say that the partial of f with respect to x is equal to 0. Why? Because the limit is 0, right? Similarly, observe that f with respect to y also exists, and that is also equal to 0. So the option says the partial derivative does not exist, which is wrong because it exists. Now it asks whether the partial derivative is continuous. So now let's look at the functional form of the partial derivative. So what is the functional form of fx, right? So if I take derivative with respect to x of f, what do I get? I get twice x minus y times sine of 1 by x minus y, right? Plus x minus y squared, then I have cos 1 by x minus y, and then I have minus 1 by x minus y squared. So that is equal to twice of x minus y sine 1 by x minus y minus, okay, we have cos of 1 by x minus y, right? This is whenever x is not equal to y, right? And when x is equal to y, then when x is equal to y, we have that, or at least we can say that this is when x comma y is not the origin, right? And when x comma y is the origin, this is 0, right? How do I get this? This was from option B. Like from solving option B, we observed that the partial derivative of f with respect to x is 0, right? So this is the functional form of the partial derivative. Now we have to check whether this is continuous at 0, right? So how do we check it? Again, we have to check whether limit x comma y goes to 0, twice of x minus y times sine 1 by x minus y minus cosine of 1 by x minus y. This should be equal to 0, right? Observe that the first term is equal to 0, so we can say this is equal to, so the limit of this term will be equal to 0, so we can write it as this is equal to 0 minus, then we have limit x comma y going to 0 cos of 1 by x minus y. Now we'll show that this limit does not exist. How do we do that? Take y equals x minus 1 by 2n pi, right? In this case, what happens is that we'll have limit x going to 0, y will also go to 0 subsequently, and then we have cos of 2n pi, which will be equal to 1. And if you take y to be x minus 1 by 2n plus 1 pi, then we have limit x going to 0 cos of odd pi, which will be equal to minus 1. So we observe that when we restrict it to two different relations between x and y, we get two different limits. So the limit L, so the limit does not exist, okay? If I call this limit L, if I call it L, then the limit L does not exist. Does not exist. So what do we have ultimately? We have that the limit, so ultimately we have that fx, or the partial of f with respect to x, is not continuous at x comma y equal to 0 comma 0. Okay. So again the option is wrong. The last option asks us to check whether the function is differentiable or not. So how to check differentiability? For two variable function. Step 1, first you start off by computing the partial with respect to x and the partial with respect to y. Compute them. Okay. Then the second step should be suppose we need to check differentiability at the point a comma b. Then the second step should be look at f of a plus h comma b plus k minus f of a comma b minus the partial of f with respect to x times h minus the partial of f with respect to y times k. Look at this term and express it, or you can say that look at this divided by under root h square plus k square, right? And the limit of this as h and k goes to 0 must be equal to 0. So this is the condition for differentiability of a two variable function, right? So now we need to do it for the given function f at the point 0 comma 0, right? So let's look at it. So we've already computed step 1, right? So step 1 we have already computed, and we have obtained that the partial with respect to x and the partial with respect to y, both of them are 0, right? So basically these two terms vanishes in our problem. So we only need to look at the rest. So what do we have? We have f of 0 plus h comma 0 plus k minus f of 0 comma 0 divided by under root of h square plus k square. This is equal to, so can be written as h minus k whole squared, right, times sine of 1 by h minus k, right? This is minus 0, so we don't write that, divided by under root of h square plus k square. So now I can write this as h square plus k square, right, minus 2hk divided by under root of h square plus k square times sine 1 by h minus k. Now let's focus on this part initially. So this can be written as under root h square plus k square, right, minus 2hk divided by under root of h square plus k square. Now observe that if you take the mod of this, right, this will definitely be bigger than or equal to 0, and it will be less than or equal to under root h square plus k square plus modulus of 2hk divided by under root h square plus k square. This is by using triangle inequality, right? This will be less than equal to under root h square plus k square plus, so now observe that uh, k square is less than h square plus k square, so mod k will be less than h square plus k square ka under root. That implies that mod k by under root h square plus k square is less than equal to 1, right? Using this we can say that this is less than equal to 2 times mod h, right? Now observe that this term converges to 0 as hk goes to 0, right? So what do we have? We have that by sandwich theorem, what do we have? We have that limit of this goes to 0, right? So what we can say additionally is that, again by using the property that sine is less than equal to 1, we can say 0 less than equal to modulus of, so let me call this entire thing g of h comma k, right? So we can say g of h comma k times sine of 1 by h minus k less than equal to g of h comma k. Again by sandwich theorem, what we have is that limit h comma k going to 0, and that entire term which I mentioned in the beginning, that is equal to 0. From there we can conclude that f is differentiable at 0 comma 0, right? So this option is actually true. So here we have the question, we have the function fx comma y given to be x to the power 1 by 3 y to the power 1 by 3, and they are asking if the directional derivative exists at 0 comma 0 in some direction. So how do we compute directional derivatives? Fix a direction, right? So say, let's say, so fix a direction. Well, let's say the direction is u vector, or you can write it as u1 comma u2, right? Because it's two variable, direction will be two variable, right? Now compute the limit f. So suppose we want to check directional derivative at a, right? Then what do we do? F of a plus t times u vector, right, minus f of a vector divided by t, and then we make t to be arbitrarily small. So this, if the limit exists, then we say that the directional derivative exists, and that will be the directional derivative along u. Okay, so this is directional derivative at a of f along u. Okay, so similarly let's look at the directional derivative at 0 comma 0. So what do we have? Limit t going to 0, okay, f of t times, so I'll write f of 0 plus t times u1 comma 0 plus t times u2 minus f of 0 comma 0 divided by t, which is nothing but t to the power 2 by 3 times u1 to the power 1 by 3 u2 to the power 1 by 3 by t, which is nothing but u1 u2 to the power 1 by 3 divided by t to the power 1 by 3, right? Now observe that as t goes to 0, this goes to infinity, right? Unless, okay, so let me just write it down. So if u1 u2 both are non-zero, right, then this limit, so let me call this limit say L, okay, then limit, or I'll just write, then L is tending to infinity, or you can say does not exist, does not exist. But if either of u1 or u2 is 0, then L will go to 0, right? Right. So the only way directional derivative can exist is when u1 or u2 is 0. What does that mean? That means either along x-axis or y-axis, right? So only the partial derivatives can exist, right? Because x-axis means u1 is 1 and u2 is 0. In case of y-axis, we have u1 is 0, u2 is 1, right? So the option says it exists in some direction, which is true because it exists in the direction of the x-axis and the y-axis. The second option says the partial derivative does not exist, which is false because we've just seen that it exists. The third question asks if f is continuous at 0, 0. So again, this is straightforward because just observe limit x comma y going to 0, xy to the power 1 by 3 will be equal to 0, right? Which is nothing but f of 0, 0. So it is continuous. So f is continuous. This is true. What about differentiability? So now observe. So note that if a function is differentiable at a point say a comma b, then that implies that all of its directional derivatives existed at a comma b, right? And this implies all the partials exist. So this is specific to a particular point. So since some of the directional derivatives does not exist at a comma b, we can say that f is not differentiable, right? Since some directional derivatives does not exist at 0, 0, what can we say? We can say that f is not differentiable. So this option is actually true. So here we have a function from R2 to R such that along the second coordinate it is an increasing function, and along the first coordinate also it is an increasing function, right? So what does it mean? It means that if y1 is less than y2, then we can say that f of t comma y1 is less than equal to f of t comma y2. Since it is non-decreasing, we have an equal to sign here. Okay. And similarly, if x1 is less than x2, then we have that f of x1 comma t is less than or equal to f of x2 comma t, right? The first option asks if f of x comma x is a non-decreasing function. So observe that if x1 is less than x2, then what we can say is that what we can say about f of x1 comma x1, right? This will be less than or equal to f of x2 comma x1, right, by this property, right? And this will be less than or equal to f of x2 comma x2 by the first property. So what do we have? We have that kx, right, which is equal to f of x comma x is a non-decreasing function, right? So this option is true. Then it says the number of discontinuities of f is at most countable, right? This is true in case only for single variable function. It does not hold in the multivariable case. Observe that if you look at this function, so take fx comma y equals 1 if x is bigger than or equal to 0, and 0 if x is less than 0, right? So how do we have this function? So if you visualize it, this is R2, right? And on the right hand side, where it is shaded yellow, the function takes value 1, and on the left hand side, when it is shaded pink, the function takes value 0. So 0, this is 1, right? This is how f looks like. Now observe that every point on the y-axis are points of discontinuity, right? Because if you approach, so let's take it a random point here, right? If you approach from the left hand side, the limit will be 1. If you approach from the if you approach from the right hand side, the limit will be 1. If you approach from the left hand side, the limit will be 0, right? In fact, it will have two different directional derivatives, right? So what does that mean? That means it is not differentiable on the y-axis. This means f is not differentiable on the y-axis, and the y-axis contains uncountably many points. So this is a contradiction to the second option. So the second option is false. So the third one says x and y both going to infinity, positive infinity, whether f of x comma y exists. So we need to look at limit both going to infinity f of x comma y. Now observe that we already had this. So look at this inequality. From this inequality, what we can say is that f of x comma x, sorry, is less than equal to f of x comma y is less than equal to f of y comma y, right? So observe that it's also given that f is a bounded function. What does it mean? It means that f of x comma y, if you take the mod of it, right, will be less than equal to m for some big positive number n, right? It also means that the supremum of fx comma y will be less than equal to m. So we also have that. So if you look at kx, right? So kx is nothing but f of x comma x. So this is also bounded. So kx is bounded, right? Again by say m, right? What does that mean? That means and kx is monotone, non-decreasing. So now we have this result from single variable calculus. We have this result saying that if a function is monotone plus bounded, so if it's monotone increasing and bounded above, then the limit x going to infinity of that function, say f, will be equal to the supremum of f, right? This is a result from single variable which will apply here, and we get that limit x going to infinity kx's will be equal to the supremum of f of x comma x, which is, let's call that supremum say s. Okay. Similarly, if you increase y, take ky, this will also be y. This will also be s, right? So now observe that by this inequality, the left hand side goes to s and the right hand side also goes to s. So what do we have? By Sandwich theorem we have that. So now by Sandwich theorem, what do we have? We have that limit x comma y going to positive infinity f of x comma y is equal to s. So the limit exists, right? So the third option is correct. What about the fourth option? It says x is going to positive infinity but y is going to minus infinity. Consider this function. So suppose this is the R2, right? Suppose consider this line. This is the line x equal to minus y line, okay? And suppose we have a function which is 0 on the left of this line right? So the function value takes 0 on the left of this line and it takes value 1 on the right side of this line, right? So f is equal to 1, suppose. So how do we write this function? This would be f of x comma y equals 1. When is it 1? When x is bigger than minus y, right? Or you can say x plus y is bigger than 0, right? And 0 when x plus y is less than equal to 0. Let's say this is our function. Okay. Then now we need to compute the limit x going to positive infinity, y going to negative infinity, f of x comma y. We'll show that this does not exist by taking two different relations on x and y. Okay. The first one which we'll consider is this line, right? So this line we consider by, say for example, uh, x plus y equal to 1. Okay, so let's take x plus y equal to 1. In that case, when x goes to infinity, y will automatically go to negative infinity, right? So we have limit x goes to infinity f of x comma y, right? But we observe that the line is entirely on the pink side, so that means the function value is 1 all the time, right? So this is, so f of x comma y, this is equal to 1, right? Under this condition, x plus y equal to 1. Now take another condition, say x plus y equal to 0, which is going through this line. So if you take this condition x plus y equal to 0, again we have that if x going to positive infinity, y will go to negative infinity, right? So again limit x going to infinity f of x comma y, right? Or you can say, to be more precise, f of x comma negative x, and here you can say f of x comma y can be written as 1 minus x. This is equal to 1 and this is equal to 0. So for two different relationships on between x and y, we are getting two different limits. That means the limit in total does not exist. So limit x going to positive infinity, y going to negative infinity, f of x comma y does not exist. So what do we have? We have that the last option is not correct. So here we have function f from R3 to R2, right? F from R3 to R2. What we'll initially do is we'll write f as f1 comma f2, where f1 and f2 are maps from R3 to R. Then it's given that g is given to be a function, and we are asked when will h admit a differentiable inverse in some neighborhood of 0 comma 0. So this is a very popular result which says that so suppose h is a map from Rm to Rn, then h has a differentiable inverse in some neighborhood of some point, say a vector, if and only if the Jacobian of h computed at a is an invertible matrix, or I should be more precise, has full rank, right? So if you look at h is nothing but f1, f2 and g, right? So what will be the Jacobian of h? In the first row you'll have the gradient of f1, right? The second row you will have the gradient of f2 and so on. The third row you'll have the gradient of g, and we need to see if this is of full rank. Okay, so observe that. So what will g be? So the last, since g is already given, we can compute the last row to be, so this is g, So gradient of G would be, if you take derivative with respect to, so we have to compute it at the point 0 comma 0 comma 0. So this would be 1 1 1, right? So the last row would be 1 1 and 1. Now observe that if the last row is 1 1 1, then obviously this will not hold, because the moment you have a row which is fully 0, the matrix A will not have full rank, right? Similarly, the second option is not true, because the first row, let's say row 1, is twice row 3, right? So it will not be full rank. The third row will hold. It is easy to check that the matrix 0 0 minus 1 0 1 0, this is a full rank, right? Similarly, you can also check that this matrix 4 2 4 0 3 2 1 1 1, this is also full rank.